The first major set of directions in the NMR module that teach you how to drive MNova all relate to the proton NMR spectrum. And the various elements involved are that you have to set a reference, you have to figure out how to do the integration, you have to find what the chemical shifts are, and then you have to measure the J values. And the end result of working through all of those steps is that you can end up with a figure like this one that has a lot of information buried within it, such that you can then fill out a table like this. And again, you're going to have chemical shifts listed, you're going to have the multiplicity of the peaks, you have to measure the J values for all peaks that are regular nice multiplets, and you have to have integration. And you need to interpret all of these well. So the integration, for example, is rounded to integers, and the J values are rounded to the tenths, and the multiplicities need to be interpreted, and so on. All of those elements are described for you in those lab manual pages. By contrast, the C13 spectrum is much simpler. There are really only two tasks before you. One is to set a reference point, which either can be the CDCl3 or TMS if present. And then the second is you need to read off the location of the peaks, find the chemical shifts associated with those peaks. And then the table associated with C13 NMR is always really straightforward. Where are those peaks? Because all of those peaks are singlets, we don't perform integration, and since they're singlets, there are no J values. That turns out not to be true all of the time. It's largely true because of the way we choose to run the spectra. But if you want to know more, there's a video that describes why we run the spectra the way we do. But for now, know that the typical C13 NMR experiment just simply will have singlets, no integration, no multiplicity, and so on. And so walking through this set of instructions, I'm going to do that in MNova now. So we're in the Chem 240 folder, we're in lab, we go to NMR worksheet, we go to 4-hydroxybutanone, we go to C13, and we open any of the files. And the standard spectrum for C13 will look something like this. And if you take a close look at what you see at first, there's just a bunch of individual single lines, apparently, with this sort of thicker version right here. And if you zoom in on it tightly, it becomes clear that this is three lines that are all roughly the same height. And if you use the set a reference tool L, then you click on that and you can set this to be 77.16. The middle of the three lines is 77.16. And now you can see that if we use the reference tool again, there it is, 77.16. And what I have done is to set the middle of the three lines of CDCl3 to be at 77.16. And that means two things. One, you should use the middle line of CDCl3 to set that reference point to 77.16, but also that you should be ignoring it. It's not part of your stuff. It is the solvent that is present in the NMR tube. Your stuff is separate from this. There is a separate reference point that we could use, and that's at 0.0, and sometimes that's a prominent peak that makes sense to use, and sometimes it's really tiny. And right now, here it is. That little guy right there could, in principle, be right at 0. We could use TMS to set that reference. But again, if I do that, if I set this to be exactly 0, and then we return to the middle of the CDCl3, you find that this is now no longer where I want it to be. And again, I prefer to use 77.16 as my reference point, if only because it is present in higher amounts right now, and it's crystal clear where that is, so I will use that as the reference. The only other major task in C13 is to find the peak picking, and that means that you come over here and you type K for the peak picking tool, or alternatively use this little tool right there. But anyway, you just click and drag, and if you click and drag across a single line, you'll get the numbers up at the top. Those blue numbers will tell you where everything is. You can do that across multiple peaks at once. I should point out that that right there is a bit unusual, that there are two lines theoretically there. If you take a closer look at the peak at 57.9, you can see why the computer might call this two different peaks, because there's a higher point over here and then a higher point over there. But even to relatively untrained people's eyes, this just looks like a singlet, and you're pretty comfortable calling it a singlet. However, and this is a separate spectrum, you can sometimes encounter scenarios like this one where it really does appear to be two different lines right next to each other. Except that you should be aware that though that's possible, it's pretty unlikely. And given the way that we tend to take these spectra, again, given the pulse sequence that we use to collect the data for C13 NMR, either this is two peaks that come exceptionally close to each other in the C13, or it's it's just some weird artifact and this really should be a singlet. How do you know which one's which? Well, ultimately, you really want to have some kind of independent piece of evidence that tells you which one is which. If your mass spec suggests to you that you have 7 carbons, and counting this as a singlet, you have 7 carbons, well, then that probably means it's a singlet. Whereas if you have 6 carbons, but this one here you're counting as 1, and it turns out you really need 7, then you might start to think that maybe, in fact, this is 7 carbons, 1 there and 1 there. But again, by far the most likely thing that's happening when you look at a C13 is anything that looks like it should be 1 line truly is 1 line. And though that doesn't have to be the case, it's more often the case than not. Closing this extra spectrum and returning now to the 4-hydroxy-2-butanone. Again, when you zoom in really tightly, you probably think of that as a singlet. But when I'm talking about this thing looks like a singlet, what I mean is zoomed out, or even zoomed to some intermediate level where the zoom window is maybe 20 or 30 units wide, and you take a look at this and it looks like a singlet, then your best bet is probably to interpret this thing at 57.9 or 57.8 as being a singlet. And that does raise another point, that what you want to do is to round to the tenths. So this is very difficult to see because of the title, but of course you can turn off things like the title if you want. If you want to be able to see the peaks information easier, come to the labels and you can change the font, and you can make the font to be much more large and visible. And what you see now is that 209.7 is the appropriate point there, 57.9-ish, 45.4, 30.6. Those are the reasonable peaks for 4-hydroxy-2-butanone. And that's really how you do this at C13. You set a reference, and then those are your peaks. Ignore CDCl3 because it's the solvent and not part of your stuff. Ignore any TMS peak if present because it's part of the reference sample present in your solvent and it's not part of your stuff.